That glowing smudge you picture when someone says comet? The cloud surrounding it, the coma, can swell wider than the sun itself. The solid chunk of ice and rock causing all of that? Usually under 10 kilometers across, smaller than a city. Here's what most people miss. There are at least 6 distinct types of comet, and they barely resemble each other. Some take a million years to complete a single orbit, making their very first pass through our solar system right now, never to return. Some dive so close to the sun they pass through its actual diameter, then either survive the encounter or vaporize completely. And some are being discovered today by volunteers at home, scanning satellite imagery on their laptops, roughly one every 3 days. In the next 10 minutes, we're covering all 6. But to tell them apart, you need to know what you're even looking at. So here's a quick anatomy check, and then the 6 types. Back in 1950, an astronomer named Fred Whipple proposed an idea that sounded almost too humble for something so spectacular. He called the nucleus a dirty snowball, a solid amalgam of frozen ices and embedded dust. For 36 years, it stayed a model on paper. Then, in 1986, the European Space Agency's Giotto spacecraft flew straight into the heart of Halley's Comet and confirmed it. By mass, that nucleus is roughly equal parts 3 ingredients: water ice, inorganic silicate dust, and organic carbonaceous material or the carbon, hydrogen, oxygen, and nitrogen particles astronomers nickname CHAN. Of all the volatile material locked inside, water ice makes up something like 75 to 80%. That frozen mud ball does nothing dramatic until it nears the sun. Then the ices sublimate, turning straight from solid to gas, and gas and dust pour off into a glowing halo called the coma, the part that can grow larger than the sun in diameter. Surrounding even that is something you can't see, an enormous envelope of neutral hydrogen created when solar ultraviolet radiation splits the comet's water vapor molecules apart. Then come the tails, plural. Most comets display 2. The first is a whitish-yellow dust tail, smoke-sized particles gently pushed back by the pressure of sunlight itself. The second is a blue plasma tail, minus electrically charged carbon monoxide ions, blown straight away from the sun by the solar wind. The two can even point in slightly different directions. Dust curves softly, plasma streams dead away. 2 tails, 2 forces. Now you have the vocabulary. One dividing line before we count them off. Every comet falls into one of 2 buckets: short period, meaning an orbit under 200 years, or long period, meaning over 200. Why 200, specifically? Because comets that return inside that window have been observed across multiple apparitions, pinning down their timetable. It's an observational line in the sand. Short period means we've watched it come back, schedule confirmed. Long period means a return no living person will witness. Hold that. 6 types, each stranger than the lastness. Here's what makes each one distinct. Type 1. Jupiter family comets. The most numerous class by far minus, as of November 2021, astronomers counted 815 of them. They have short periods, under 20 years, and low inclinations, tilted no more than about 30 degrees from the plane of the planets. And they come from the first of our 2 cosmic freezers, the Kuiper belt. It begins just beyond Neptune, stretching from about 30 to 50 astronomical units from the Sun, 1 astronomical unit being the Earth-Sun distance. The belt is flat, lying in the same plane as the planets, packed with millions of frozen objects left over from the solar system's birth. The reason these comets behave so predictably is the giant standing guard. Jupiter's gravity acts like a bouncer, capturing them and shepherding them into tidy short loops. The poster child is Comet 67P/Churyumov-Gerasimenko, with a period of 6.45 years. A Jupiter gravity assist in 1840 first nudged its orbit, and a larger encounter in 1959 kicked it into the tighter loop it follows today. In August 2014, this rubber duck-shaped lump of ice became the most studied comet in history when ESA's Rosetta spacecraft became the first ever to orbit a comet and then to drop a lander onto its surface. What it found was staggering. Glycine, an amino acid. Phosphorus, a building block of DNA. Molecular oxygen, detected at a comet for the very first time. And water vapor with a deuterium to hydrogen ratio 3 times higher than the water in Earth's oceans, a clue that not all comets delivered our seas. Hold on to those ingredients, they matter at the end. Type 2. Encke-type comets. The Insiders. Here's their signature. Comet 2P Encke is the parent body of the Torrid meteor shower. The debris we plow through every autumn is shed straight off this object. As a class, they're defined by their orbits. Their farthest point from the Sun, the aphelion, lies entirely within 4 astronomical units, inside Jupiter's orbit. They never even reach the giant planet. 74 are known. And Encke itself holds a record nothing has beaten, the shortest orbital period of any known comet, just 3.3 years. It swings into a perihelion of 0.34 astronomical units, closer to the Sun than Mercury's average orbit, and was first recorded by Pierre Méchain on January 17, 1786. Type 3. Halley-type comets. The rule breakers. Their periods run from 20 to 200 years, and unlike the well-behaved Jupiter family, their inclinations are all over the map, meaning from 0 degrees to past 90, which means some orbit backwards, retrograde, against the grain of the planets. There are 109 known. And crucially, they come not from the flat Kuiper belt, but from our second freezer, and it is almost beyond comprehension. The Oort cloud is a vast spherical shell wrapped entirely around the solar system, stretching from roughly 3,000 astronomical units out to 100,000, nearly halfway to the next star. Inside it drift an estimated trillion to 10 trillion icy bodies, with a combined mass of about 100 Earths, divided into an undisturbed inner zone, a middle zone tugged by the galaxy's own tides, and an outer zone so loosely bound a passing star can shake comets loose. That spherical origin is what gives Halley-types their wild tilted paths. The legend, of course, is 1P/Halley. It returns every 74 to 79 years, call it 76 on average. Its nucleus is about 15 kilometers by 8, and it is one of the darkest objects in the entire solar system, reflecting as little as 4% of the sunlight that hits it, about as dark as coal. When Giotto flew past in 1986, it found only about 10% of the surface was actively outgassing, the rest sat dormant. Halley is the only short-period comet reliably visible to the naked eye, and we've watched it a very long time. The earliest confirmed sighting appears in Chinese records from 240 BC, but it was Edmund Halley who, in 1705, cracked the pattern, proving the comets of 1531, 1607, and 1682 were one and the same object, and boldly predicting its return in 1758. He was right, though he didn't live to see it. It last graced our skies in 1986, and it will return in mid-2061. It still leaves us gifts twice a year. The Eta Aquarids in early May and the Orionids in late October are both made of Halley's shed debris. Type 4. Long-period comets. The once-in-a-lifetime visitors. Their periods exceed 200 years skyness, but that's just the floor. Some take 100,000, even 1,000,000 years to circle the Sun once. They fall in from the Oort cloud, arriving from completely random directions across the entire sky. And that randomness is our proof the cloud is a sphere and not a disk. If these comets came from a flat ring, they'd cluster near one plane. They don't. They come from everywhere. On July 23, 1995, 2 observers, Alan Hale and Thomas Bopp, independently spotted the same faint smudge on the same night. That smudge became Hale-Bopp, Comet C 1995-01, and it was a monster. Its nucleus measured about 60 kilometers across, roughly 6 times larger than Halley's. It hung in the night sky, naked to the eye, for a record 18 months, twice as long as the previous champion, the Great Comet of 1811. An entire generation remembers it. But notice the catch. Long-period comets may return Manus in 100,000 years. The next type cannot. And the difference comes down to one number: orbital eccentricity. Hit exactly 1.0 and you're on the razor's edge, exceed it, and the path never closes again. Type 5. Hyperbolic comets. The one-way tickets. These travel on parabolic or hyperbolic trajectories made eccentricity of 1 or greater. In plain terms, the orbit isn't a closed loop, it's open. A hyperbolic comet makes a single pass through the inner solar system and is then flung away permanently. These are dynamically new comets, long-period bodies falling sunward for the very first time, tumbling in from the outer reaches of the Oort cloud after billions of years in total darkness and total silence.